everybody. I would like to thank the organizers for the invitation to give this panel talk, and I'm really delighted to be here with you. I'm sure we're going to have very interesting presentations and discussions here. So I'm going to present our view on cognitive radio, the operator's perspective as far as Orange is concerned. And this is a common work with my colleague, Vladimir Bouquet, who is responsible of the spectrum issues in Orange. So I'm from the research department, so this work will be a mixture of research and regulation issues. So the outline of my talk will be as follows. First, I'm going to give a brief background of cognitive radio with an overview of possible deployment scenarios that we see around today. Then I'm going to mention a little bit what we think about the maturity today of opportunistic spectrum access. Then the third part, I will go into the details of our perception on cognitive radio. How do we perceive and what are our propositions for cognitive radio systems? The opportunities that the operator can see for cognitive radio. And finally, I'll conclude and give some perspectives on cognitive radio systems. So we all know this famous cognitive cycle proposed by Joe Mitola about more than 10 years now, 10 years ago. So it's, in fact, if we read carefully the PhD thesis of Joe Mitola, we see that he's not talking about a signal radio, but he's talking about a system of radio devices that are intelligent, that are capable of doing cognition as far as the user desires and user is concerned, and is capable of taking actions in an autonomous manner. So that's why I prefer to talk in terms of cognitive radio systems rather than a cognitive radio by itself. So cognitive radio systems are a set of radio equipment that are aware of its surroundings and adapts intelligently. This is a huge definition, so we can put a lot of things in that. And when we look around, when we see how the term cognitive radio is loaded, that now, as Petri had said a couple of years ago, we can now say cognitive communications, this is the wireless communications. So everybody is talking about cognitive radio, and now we have the impression that wireless communications is becoming cognitive communications. Here I have put the ITUR definition of cognitive radio. So what do the international regulatory body thinks about cognitive radio? So they say that this is a radio system employing technology that allows the system to obtain knowledge of its surroundings. So that's what we call the environment awareness. They are aware of established policies and the internal state. The system uses this knowledge to dynamically and autonomously adjust its operational parameters and protocols according to the knowledge that it has in order to achieve predefined objectives. And the most important thing is that the cognitive radio learns from its experience. So since the term has been around for more than 10 years, we have seen a lot of deployment scenarios around. So we can group those deployment scenarios in 5 main categories. The first one is the cognitive radio technology used by an operator and only by an operator to manage flexibly and optimally its own spectrum resources. So that's what we call the intra-operator scenarios, where there's only one operator, a license holder, and that uses the cognitive features, cognitive principles, to better manage its spectrum resources. So this is more or less what we have today, with some exceptions. If we relax a little bit, then we come up to the second group of deployment scenarios, where we have spectrum sharing between several operators, but with a priori agreements. So several operators get together, make some a priori agreements, and they share the spectrum. Going one step further through a liberal scheme, we arrive at the third scenario, where we have the opportunistic spectrum access among several operators, but without a priori agreements. So this is really opportunistic, and there are no a priori agreements. I think this is the most popular scenario that's been around, especially in the academic environments, and what we call as opportunistic spectrum access, and whose embodiment today we see in white spaces. The fourth one, we can use cognitive radio features, what cognitive radio can offer to guide terminal reconfiguration in a heterogeneous radio environment. So this calls for what we name as software-defined radio, and we can use the cognition to optimally configure the software-defined radio of terminal equipment, where we have several radio access technologies around. And finally, we can use cognitive radio technology to collaborate between public and private radio systems. So now I'll briefly talk about the opportunistic access and our view on that. So the embodiment of the concept of opportunistic radio access today is known as TV white spaces. We all know what it is. Well, the formal definition is given on the slide. So first of all, it's a piece of spectrum that's available for radio communications that's not used by the primaries or by the license holders, and it is time and space dependent. It must not interfere, it must not cause harmful interference to the existing radio technologies, and it cannot claim any protection with a higher priority on a national basis, and here we're talking about the UHF television band. So we think that this is a very interesting concept, but there are still a lot of challenges in order to come up with a mass market product. There are still technical challenges, although there has been a lot of technical work done since more than 10 years. So when we look at the academic literature, we see a lot of papers, a lot of nice work done, but we still lack robust and reliable technical solutions for that. So there still remains technical challenges to solve. I'm not talking about non-technical challenges, I'm going to come to that, but there still remains. So reliable detection of the incumbent users is still a problem. Practical solutions for example, hidden node problem is not yet solved. Or, for example, in TV white spaces, solutions to detect PMSE devices, the microphones, are not yet mature. So that's why FCC has decided to allocate 2 channels for PMSE devices. So this is not TV white spaces. At the moment, there are 3 techniques used for detecting the incumbent services that we can see here. If I can use the pointer. No. So here on the right-hand side at the bottom, there are 3 basic technologies that is proposed: sensing, pilot channel, a common dedicated pilot channel, and geolocation and database. But we think that now it's time to go beyond that vague and generic term of saying this mustn't cause harmful interference, really quantify on a case-by-case basis what does it mean, harmful interference, what are the implications of not causing harmful interference, and really come to a common understanding of what it means. Otherwise, we're going to get stuck in where we are today, because a common understanding of what it means, harmful interference, is not yet established. Another very important issue is security, and this is also identified by one of the glass ceilings of cognitive radio technology by Joe Mitola itself. The security issue is a critical issue that must be solved in order to have a cognitive radio system deployment today. So that's exactly our perception also. One more slide on TV white spaces. The availability is questionable. So we're not sure whether we're going to have available channels everywhere, every time. It may be available sometime, it may not be available 10 seconds after. So this is a problem as far as quality of service is concerned, but as far as having a common dedicated channel is concerned. So people talk about having a dedicated common channel based on internet access, but if we have internet access, then why do we need white spaces and things like that? Another thing about availability is probably in the Sahara Desert we have an enormous amount of white spaces, but there's nobody to use it. So where TV white spaces are available, the business prospects are not that good. But when we have high demand for traffic, the availability is really questionable. So another issue is to have concrete, good business plans. Otherwise, even if technically feasible, we're not going to have a TV white space deployment as a mass market product. Due to all those reasons, before attributing a certain band of spectrum as unlicensed to be used by TV white spaces, very careful considerations has to be carried out, involving all those steps that I have mentioned. So far for the TV white spaces. Now I'm going to talk a little bit on our perception of cognitive radio. After all mentioning all those obstacles and challenges on opportunistic access, do we say no to cognitive radio? No, we don't say no to cognitive radio, because what we perceive as cognitive radio is not only TV white spaces. TV white spaces is not cognitive radio. Cognitive radio is something much more broader that everybody can make use of. Even a license holder operator can benefit from cognitive radio. So we end up with this intra-operator spectrum management scenarios where a single operator can make use of cognitive radio features to perform flexible and dynamic management of its own spectrum in order to adapt to changing traffic conditions, in order to optimize his carrying of traffic by an intelligent use of the spatial and temporal variations of traffic. and in that ways optimize its spectrum utilization in an autonomous and flexible manner. How can the operator do that? An immediate benefit that we see is provided by geolocalized measurements. We already have a lot of measurements in the network. An operator has an enormous amount of measurements. And more now we see the penetration of geolocalization with all those applications. Now every smartphone has GPS embedded in it. And we see more and more the penetration of the concept of geolocalization in the wireless world. So why not make use of it in order to identify those temporal and spatial variations of traffic and adapt the resources accordingly? So this is the first thought that we had, and we think that it has immediate benefits. First of all, these geolocalized measurements provide that environmental awareness of cognitive radio. And processing intelligently these geolocalized measurements, we see that we can benefit from the cognitive cycle, putting into learning also in the picture. So what I'm going to present you here, that a concept called as radio environmental maps that makes use of the geolocalized measurements, that provides that environmental awareness for the operator. And it's a cognitive tool that we have been studying on since a couple of years. Basically, we have geolocalized measurements. And what is a radio environmental map? We process those measurements according to an underlying model, and we have some predictions at places where we do not have measurements. So at the end, we have a realistic map of the environment. However, we load this term environment. It can be propagation, it can be traffic, it can be some quality of service perceived by user. But whatever it is, it's very useful for the operator, because the operator has a temporal and spatial view, a realistic temporal and spatial view of the environment, on which it can work and do optimization. First of all, doing measurements, such measurements as drive tests, is very expensive for the operator. So by combining the measurements and the model and the realistic model, it reduces the requirements on the measurements, so it immediately provides an OPEX gain to the operator. And we can also have some dynamic updates, because we continuously have measurements coming from the network, so we can update the map and have an up-to-date picture of the radio environment. So how can we use those REMs? We have identified some scenarios. In fact, we have been working in the FP7 project Faramir on radio environmental maps. And in Faramir, we have identified a lot of scenarios. Here I'm just going to mention a little portion of that concerns the intra-operator scenarios. But there are a lot more scenarios in which we can use REMs. So here are a couple of scenarios. We can just do network optimization based on key performance indicators, what we call KPIs, based on REMs. It can be mobility optimization, any kind of optimization that the network operator is doing today, based on KPIs. We can do self-configuration and self-optimization of femtocells, which they are supposed to be plug-and-play devices. So such radio environment awareness can play a crucial role in optimization of femtocells. Refarming is something that we do regularly. This is recycling of the old technology bands by deploying new more spectral efficient technologies, like, for example, UMTS 900. And relays, which are an indispensable element of LTE advanced technology, can benefit from REMs. So this is a picture of how can we do troubleshooting and optimization using REMS. So we have measurements at certain places, but we do not know the actual coverage hole. So by doing this interpolation and having these predictions at places where we do not have measurements, we can have a more realistic knowledge on the real coverage hole and do our optimization accordingly. So REMS in that sense can provide us with cognitive means to optimize the solution deployed by the operator to cover that actual coverage hole. Femtocells, as I have said, they are, I think, the first cognitive devices that we see today, because they are partially out of control of the operator. They are operated by the users, so the operator doesn't know when and where a femtocell will be deployed, will be set on. So in that sense, they must be cognitive. Here, for example, a typical scenario can be the orange guy doesn't know the existence of the blue guy, but thanks to the environmental awareness provided by REMS, the orange guy can be, and it's true for the blue guy also, they can be aware of one and each other, and they can optimize their transmission powers accordingly, not to cause interference to one another, and to optimize their coverage areas also. It's valid for macrofemto existence also. Actually, how do we do refarming? We create some buffer zones geographically and some buffer bands in the spectrum in order not to create interference between the new deployed technology and the old one. But of course, in doing that, in order not to create any interference at all, we always consider the pessimistic scenario, and we usually overshoot in guard bands or in buffer zones. If we have a realistic map of the environment, we can optimize these buffer zones or guard bands in order to minimize the waste of resources, because buffer zones and guard bands are a waste of resources. So this is basically a coexistence planning of the old and new technologies. Well, the relays are more and more interesting for the operator because they can provide solutions for coverage and capacity optimization. And having a realistic knowledge of the coverage zone to be covered by the relay or the traffic hotspot that is going to be served by the relay is important, and geolocalized measurements through REMS can provide the ideal information for the relays to adjust their transmission parameters to cover the zone exactly. Because if it is covered more, it will create interference. If it is covered less, it will create coverage holes. And finally, our view on cognitive radio. First of all, we have this very strong message that cognitive radio doesn't mean TV white spaces. Cognitive radio doesn't mean dynamic spectrum access nor opportunistic spectrum access. It means much more. We are working on some scenarios, intra-operator scenarios, where cognitive features can be used by the operator. And we think that self-organizing networks that are being now, that has been standardized, that are now being standardized and now being deployed in operators' networks are the first baby steps of cognitive radio systems. And last message is that really before tagging a spectrum, part of spectrum as unlicensed, we really have to be sure, thoroughly discuss and evaluate with every perspective, because once tagged unlicensed, it's almost impossible to step back. So that completes my presentation. Thank you very much.
Thank you very much. We do have time for one quick question, if there is one. we'll have plenty of time afterwards as well, but if there's one quick one now, we can take it. Okay, so I think, oh, there's one.
I'm Gabriele Di Benedetto. Thank you very much for being here today with us. A provocative question. So I don't think that the argument of if something is useless, we might as well get it, right? So when you talk about TV white spaces, and your argument was maybe in a desert it's useless, then we might as well get it. This is why I think that there is some kind of trend in the evolution that cannot be avoided. It's not because something is useless that it's not going to happen, and then it opens up. So I think this is the trend, which is not driven by how useful a paradigm might be.
Well, my point in saying that was not, of course we can get it, but the problem is that who's going to put money for that?
Yeah. Okay, so first we need to have the possibility of doing it, and this is what opens up. So
yes, of course.
Just a provocation.
Yeah, that's why I said there are technical aspects, but there are also business aspects which are as important. So solving technical and business aspects are necessary in order to have a deployment. This is just the point.
Okay, so thank you very much again. I think we'll pass to the next presentation. We're going to invert the order a little bit, so I think it'll be Carlos' presentation now from
I think I can take this one. Okay, thank you very much for the kind invitation here. It's really a pleasure for me also to talk to you regarding the evolution of mobile broadband, and by that I mean basically also IMT evolution. So I'm not going to elaborate too much about TV white spaces or unlicensed frequency bands, but also take the perspective of Werner and the evolution of classic operator networks. Where to? This one? Right. Yes. Okay. Here is an outline of my talk. I have divided into three basic parts. First of all, I will just give a few trends of future radio evolution, and then turn to dynamic spectrum allocations, a few aspects of dynamic spectrum allocations and or assignments within future LTE networks, IMT networks, and then also focus a bit on self-organizing, so similar approach as we have just heard before. Then let me start up with a glance at the evolution, the big data take-up. I'm pretty sure you have seen such slides anywhere and everywhere. So there's first of all the uptake of subscribers, but these subscribers, they become more and more bandwidth hungry or data hungry. All the mobile terminals, the smart terminals, but as well as the mobile laptops, they become more and more data hungry, and there is a proclaimed huge data uptake towards the next decade. So this depicts just a normal market forecast up to 2015, but if we prospect this further on into 2020 and beyond that, we expect even more exponential uptake. And we have to be prepared for providing gigabyte for each user everywhere, at least in the hotspot areas, at least in these areas where the demand is. And for this, in order to prepare, we have to prepare the networks. We have to provide the necessary data capacity. oh, sorry, that was a bit too fast. So, where are then the basic challenges of future networks? First of all, if we focus and if we look into the behavior of data and the demands, then we realize that the challenges, the data demand is very, very uneven. It is not as it used to be in the classic voice-centric networks. These plots, where do we have? Okay, it seems not to work. These plots of data demands were not, by far not that colorful, and there were not so many small areas with huge data demand, other areas with just a low data demand. So it turns out there will be a myriad of cells with totally different technology demands and traffic demands. There may be a small number of cells, around about 10 to 20%, which cover or which carry 50 or even more of the entire traffic within a deployment area. And there are other cells which carry just quite a small amount, but nevertheless they are also necessary. They are necessary really to provide the full coverage, because if I want to travel outside, if I leave my home base where I might have a Wi-Fi which large data demand, data provision, if I go outside, I want to have kind of seamless continuity. I want to access the network with my smartphone, also when being abroad, when traveling, or just walking and roaming. So there is a kind of a change in the total requirements, and these are things we have to cope with. Then let me come to the next point. There are certain boundaries. If we want to deploy and if we want to build up our networks, of course, we still have to obey the laws of physics. We still have to obey, and here I totally agree also with Bernard, also the business aspect. There are three important gentlemen depicted here. First of all, we have Claude Shannon, who gave us the famous law of capacity and traffic information theory. We have to obey the laws of electromagnetic waves, of the propagation and the creation of interference of electromagnetic waves. And Adam Smith, he put down the basic, I think he was the first one who put down the basic laws of economic behavior and economic things. And I fully agree, without business perspective, there will be no investment. Nobody will be really ready to build up the networks for large, huge amounts of data, still maintaining a certain and a reasonable coverage. So there are the challenges to combine all these things together, to have business perspective, and on the other hand also build the networks for the data provision. We think that the basic challenges of the next 10 to 15 years will be that there will be 10 to 100 times more base stations, basically small cells. There is a huge potential in small cells, and I think this will be key solution. I'm elaborating about this a little bit more later on. The requirements will be that the data rate as such will become 10-fold or even up to 100-fold higher, and we have to cope with this by much higher spectral efficiency. But also here there are certain limits. I still have personal doubts that we can go much beyond 10 bits per second per hertz or something in that area. Currently we are still a decade or nearly a decade below that. Good. Then let's go on. Let's come to a few aspects of dynamic spectrum sharing, having also the perspective of IMT networks, LTE networks. Let's apply a first simple physical law, look into Shannon's formula. There is that, okay, if we need data, if we want to provide huge amounts of data, we need large amounts of bandwidth. That's really right. Bandwidth is a key issue, but bandwidth is not all. Even if we had unlimited bandwidth available, if we make a limit theorem tending bandwidth to infinity, it turns out that it is still the receive power which is crucial in order to transport capacity, huge amount of data towards the cell edge. We cannot afford simply to transport 1 gigabit per second towards the cell edge of a macro cell. It's impossible with the receive power we usually have at a macro cell because we simply cannot afford to transmit power for these large distances, neither at the user device due to battery issues, but also at the base stations due to some other limitations, regulatory limitations on one hand, and also on the other hand due to cost reasons. So there is no way around small cell deployments if we want to go up into huge amounts of data into 1 gigabit per second downstream or even higher. And 1 gigabit per second has been defined as a requirement of IMT Advanced in the last World Radio Conference. So it is something where at least we should have the capabilities to pick up. I'm not saying that we as human beings will consume this big amount of data all the time, but nevertheless we should have capabilities. A base station should have the capabilities to serve simultaneously several users which are simultaneously taking a large download, and that should be done within a couple of seconds because the user will demand not to wait too long for his application. And then a few seconds later the channel may be available for others. So the future challenges will be also in the area of providing large data amounts, and there is no way around deployments of local cells, of femtocells and picocells in order to cope with this. Again, I'm not saying that we can get rid of microcells, that you can get rid of macrocells. Definitely we need it. We also have to further develop them, and we have to optimize them and to use them in an optimized manner. But the huge data will take place in the pico and femto area. And still there is bandwidth needed, chunks of bandwidth, 100 megahertz or even more. And who of the operators has a chunk of 100 megahertz available? Nobody. The spectrum, again, here. The spectrum that is available on the IMT map is quite fragmented. It is very nice and very good for voice-centric and medium low data, medium and average data networks. But nowhere there's really chunks of spectrum of 100 megahertz, even of 50 megahertz or something else available per operator. Of course, you can groom this bandwidth, you can collect it somewhere, but this is not the optimum manner. So we also have to look where do we deploy which frequencies do we use for future small cells. And here there is, for instance, in the IMT map identified in the last World Radio Conference, the 3.5 gigahertz band. It is still partially used by satellites. There are partially deployments of fixed broadband wireless access, but nevertheless these frequency bands around 3.5 gigahertz up to, in Europe, in the CEPT countries, up to 3.8 gigahertz have been IMT identified, and there are huge potentials also for operating a real chunk of spectrum, providing huge amounts of data. And should we totally subdivide this when it comes to making use of this for operator networks? And here I dare saying that we should go into more cognitive, more sharing applications also here in the IMT arena, particularly for such new frequency bands. I'm not saying too much about sharing in the classical deployment areas of the macro cells. Definitely this runs into trouble. But for new potential frequency bands, I would advocate for frequency sharing in an optimized cognitive manner. And taking this I come to a principal concept of frequency sharing for small cell deployments. I also would advocate here for using central database policy service, which can create more an overview over the entire behavior, over the entire environmental conditions. Collecting data, I'm not saying that we should not also support this by usual measurements or by measurements from the base stations, from the E-node Bs as well, but in general, creating a central point of knowledge for creating this awareness and for aiding the decision making, that would lead to an optimized utilization and for frequency sharing among several cells. And here this can, if it is done in this manner, then it can of course be done also among several operators. And key for such large bandwidth sharing are future IMT bands, for instance 3.5 gigahertz, and that I would really advocate for making use of an optimized use and joint sharing in these areas. So now let me switch back. There was an interchange in the order of my slides. Then let's come to a bit of cognitive and cognition. Basically, we have already highlighted it and discussed it several times, so I'm not repeating Mitola's game here. Just the point I'd like to make is that everything we have in LTE, we have in LTE Advanced, is quite well prepared for adopting optimized cognitive innovative functionality. The user devices, the base stations, they have capabilities for doing measurements. They are used to reporting back in the network. We do have architectures with base stations, home location registers and these things, which are also prepared for sharing data in a different manner, for instance, for international roaming and these things. And it is an easy step also to take advantage of such architectures, of the basic architecture of these things, to build these towards more cognitive functions, to create the overall awareness over the network. And here I also totally agree. We cannot speak about a purely cognitive radio. We have to speak about cognitive radio systems, and this covers the architecture of the deployment. It covers the user devices, the base stations, and it covers also the network. The network has to aid these decision making. There should not be pure decision making by the user devices alone. Where are then the challenges? There are still significant challenges in the PHY layer. We have to provide the frequency agility, and here I'm also not just focusing on the frequency agilities within a small frequency range. I'm talking about large frequency coverage about over several frequency bands over a certain area of hundreds of megahertz, and this frequency agility, the bandwidth scalability, this must be available and it must be developed. Forget about all the cognitive radio, all the cognition and these things if you are not able to provide the front end, the RF front end, and also the rest of the PHY with enough frequency agility and enough flexibility. And there are still challenges. It is also a matter of cost. If you want to do everything that can be done software defined, then it is by far much more expensive if you than if you clearly integrate things more in a fixed manner in an ASIC, also the frequency dependent devices. So there are challenges which we have to cope, but nevertheless, I dare say that also LTE is quite well prepared and on track for flexible frequency functions in the PHY as well as in the MAC layer and in these things. First of all, if we look at the initial definition of LTE, we have right from the first definition a number of several base bandwidth defined, starting from 1.4 megahertz bandwidth up to 20 megahertz bandwidth, which each terminal should have the capabilities to adopt. Initially, this was just defined as a frequency bandwidth scalability, but it is an easy matter also to further develop this and changes towards totally scalable or flexible bandwidth switching, going from one bandwidth to another bandwidth, and this helps very much also in a way of dynamically selecting bandwidths in optimizing the frequencies and the band coverage within macro cells. So for intra-operator sharing of macro cells, for optimized use of the bandwidth and the frequency which an operator has available within his classic deployments, where he wants to do frequency refarming, where he wants to optimize the traffic among several RADs. You may think of that he operates HSPA networks in parallel to LTE and these things. So these frequency scalability and flexible things are of real benefit for optimizing classic deployments in refarming manner. When it then comes to large bandwidth, we have the famous carrier aggregation function, which has also been defined in LTE. The background was basically that the requirement of IMT Advanced requested 100 megahertz bandwidth adoption. On the other hand, there should be the backward compatibility with LTE Release 8, Release 9 terminals, which have the capability going up to 20 megahertz. And out of this, this carrier aggregation concept was born. And then it was also expanded. It need not to be adjacent channels just in one chunk of spectrum, but we can also collect and aggregate carriers of several frequency bands spaced apart. So this concept of carrier aggregation is quite a good preparation for flexible frequency adoption. And bringing in a bit more of cognition function in this, there have already been research concepts and algorithms towards this autonomic selection of carriers among a number of E-node Bs which may impact each other, which are deployed or which may be deployed in the vicinity of each other. There have been protocols defined how to communicate with respect to autonomous decision making here and assign the primary frequency carrier and secondary supporting frequency carrier among these nodes, and changing this in a flexible manner according to the traffic demand, so that the carrier once occupied can also be given off when the traffic demand goes down. So, in summary, LTE as such is quite well prepared for dynamic frequency selection functions. Now let us look at a few regulatory aspects. We do have the classic licensed frequency area, where frequency spectrum is assigned to the operator in a protected manner, and he wants to make optimized use out of this. We also are aware of the totally unlicensed utilization of certain frequency bands. So, for instance, the Wi-Fi bands, also the 5 gigahertz bands, and then comes the TV white spaces in addition, which among the secondary operators is also unlicensed. And particularly for the other utilization, the utilization among operators and sharing of small cells, I would advocate for some new model, regulatory model, which enables frequency sharing among operators, and not among each and everybody, just based on a certain agreement among 2, 3, or 4 operators, which can be well managed and controlled via central databases. There are such regulatory models in place, and discussion termed authorized shared access. The initial meaning of authorized shared access was also towards utilization of satellite bands, where a satellite incumbent has the right of certain frequency bands. They are kind of reluctant to give any rights away here, but when it comes to business, when it comes to kind of mutual agreement, then I would see good options also on such a basis that with an agreement among a satellite incumbent and an IMT operator, that temporarily or partially such frequencies can be utilized. And if it is just the joint utilization of primary assigned frequency bands among several operators, I would term it co-primary sharing, and these things are licensing light. That depends where we are, and these are not established regulatory models, but there's lots of discussions around this, and I think this offers quite some potential for the kind of interoperator frequency sharing. And I'm advocating here to do this basically for the dynamic sharing of small cells and picocells, not for the macro cells. For the macro cells, I think it is just worthwhile and good to use these cognitive functions in order to optimize in an intra-operator manner the own frequency bands for refarming and traffic distribution among several RADs. So, looking at these 3 licensing models, I would say considering cognitive utilization, we see quite a smooth evolution by cognitive functions in the classic licensed frequency area. We would see revolutionary gain potential in the interoperator sharing of small cells in new licensing models, just sharing among several operators. And there is some potential also in Wi-Fi frequency bands or in TV white space, a secondary usage, which then among each other is also unlicensed. But here the benefit, I would say, is available, but to a certain degree also limited, because there is no quality, and the security aspects, as Berner has also pointed out, are not really solved. So then let me come to the last section, self-organizing and cognitive evolution. We have already talked a lot about more cells, a huge amount of femtocells, of picocells. We also do have to look into several RADs being available. There are operators who operate HSPA, UMTS networks simultaneously with LTE networks, and of course there is also still the classic GSM available. And somehow the traffic and the traffic demands towards these several RADs has to be optimized, has to be shifted, and has to be refarmed. And when it comes to a huge uptake of small cells, then there is no way around in optimizing these in a totally autonomous way, in an automatic way. And this has already been kicked off a couple of years ago. There are solutions available also in standardization for self-organizing networks within the 3 dimensions: self-configurations, plug and play, self-optimization, traffic steering, power saving, interference optimization and these things, and self-healing. So there are standards ongoing, and there's huge development ongoing in that way in order to manage several layers and several hundreds and thousands of cells within an area. And this is the potential for cognitive evolution. Again, we have to talk about networks. We don't have just to focus on purely on the radio. We have to consider the architecture, the base stations, the networks, and the user devices. And it is the challenge and it is the task of cognition to create this kind of awareness into Sun and make this self-organizing, intelligent following up and optimizing. There are additional functions, for instance, or options, dimensions, active antenna, which also provides a certain resource, another dimension of resources that can be or is included in self-organizing. Here, beams can be steered, can be changed and formed in a vertical and a horizontal manner, and this can be adapted following the need of the traffic. And this entirely provides a huge potential to make it cognitive. So then let me summarize. We'd say the future networks, they will become heterogeneous. It will be dominated by small cells. But everywhere we do see a big potential for cognitive evolution. We see the cognitive, say, smooth evolution in the large wide area networks in an intra-operator manner, just optimizing the networks. We see the revolution in the very small cells, also combining picocells, which are under the full control of the network operator in his network, as well as femtocells, which are in the control of the private operator, but if they connect to the network, they can also be included in this management. So there we see a revolution, and we see that cognitive capabilities are just starting to enter this area and lead to an optimized network. Thank you.
Okay, thank you very much, Gaius. That was a very interesting presentation. I think we have time for one or two quick questions. I see one over there.
Okay, my time to try. Also, Berna can comment. So the Gabriela was not totally successful with the controversial question. So I'll try again. So I have a two-part question. The first is that let's play that I leave my job in university and go to regulator. So why I should give a 500 megahertz or 100 megahertz for NSN customers? Because I heard that at maximum you believe 10 bits per hertz as a spectral efficiency, which I don't believe. But let's play 10 bits per hertz. 500 megahertz is 2.5 gigabytes per second, and if I believe your traffic explosion and a claim that we need a 1 gigabit per second per user, so I'll give you a 500 megahertz of very valuable beachfront, and I'll serve a 2.5 customers per time. So isn't this clear that actually the only way to provide that capacity is just to go to microcells, and you don't have actually at all the frequency lag, because you can't solve the problem of having more frequency. But this is not a controversial question. The real controversial point is that I'm asking an advice, since LTE is having a huge spectral capacity, it's able to do self-organization, it's ready for cognitive. So what universities should do now next? Clearly we don't need to anymore do cognitive. So any idea from industry where we should head next?
definitely I'm not of the opinion that the problems are solved, particularly the cognitive functions. I said we are right at the beginning of introducing these things and say optimizing or creating algorithms of intelligence to really dynamically assign the spectrum, assign the resources, not only the spectrum, but also other resources like space and these things in an optimized way. I'm also not claiming that the ultimate solution is IMT networks only. There will definitely be a combination. I'm not, say, abandoning Wi-Fi networks in the home domain, or I also included kind of offload or combination of traffic making use of unlicensed frequency bands. So I think there's still a huge area to do. The only message I'd like to bring over is that cognitive as such is not just only focused, as sometimes in the academic world, so far on unlicensed only, on user devices making their own decisions, ignoring what is in the network, or just taking the decision based on their own measurements. We have to consider the entire system as a cognitive engine, and there's still a huge amount of problems to be solved. This is not done yet.
I'll still kind of challenge, but this I can't pick the fight with Bernard. The more and more what I see in cognitive, it's a good old wireless. I mean, if it's taking an input, some kind of algorithm of deciding what is the status and it act. This, when I was in a school, it was called a control loop. And when you globally optimize in several control loops, when I still was in an industry, it was called radio resource manager. So have we actually just renamed what we have been doing the last 30 years? With fancy name. I mean, I agree, it's a hell of a fancy name.
Yeah, there is quite a danger that we just rename, say, the control loops as cognitive, but this is not what makes cognitive as such. We should not forget to bring in, of course, the intelligent functions to come up with the decision making which is based on learning. So we have to take history into account. We have to see, first of all, to create the overall awareness of a situation, and this is what the control loop doesn't do. It just compares one single parameter, or possibly two parameters, are they above or below a threshold, and then reacts go up or go down. But creating a more intelligent awareness, taking the history into account, and based on my own decision making and the response I received from the network, making a new decision. I think this is the cognition we still have to enter here, and there's a huge area still for research.
I don't want to hawk, but I mean, you see, I'll try to stir up the controversy. I don't believe half what I say, but I mean, this is not cognition, how the AI community or the neurological community think. We have actually a very good estimation theoretician, Arne Mämmälä, there. So I don't, again, agree with your point. If I have a channel estimator, if I have 15 taps, it actually looks history. We have lots of physical layer technologies and network technologies with long time have been looking at history. And still these were 20 years ago called control loops or protocols. Using a historical statistics doesn't make something smart.
No, it's a certain degree of intelligence it must take on. Learning from the history. Learning a control loop always takes the same decision based on certain facts.
No. You, for example, you can have an adaptive power level which is changing its threshold.
Then it's coming. Then it's slowly or surely becoming cognitive. Slowly but surely. This is the initial steps.
I think this discussion is extremely interesting, and it'll be very fruitful for the 40 minutes at the end if we continue it. I think that would be good, because we have to.
Okay. Thank you.
Go ahead.
I think the real cognition is something like that. For example, when I'm at home and trying to read my emails or trying to finish something on the internet, and when the computer hears the baby crying in the other room, it slows down automatically the internet connection so that I get up and deal with him.
Okay, thank you very much. So I think we're going to continue now with the next presentation from Vsevolod Borzanski from Telefonica.
It's okay like this. Well, hello, ladies and gentlemen. Thank you to the organizers for the chance to be here, and very especially to the CTTC staff who have always been very kind to me in the past. So, I'm going to give a talk on a perspective on white spaces. So, as it is a perspective, I'm going to be looking at the forest and not stopping at looking at the individual trees. So, let's see if this works. How does this work?
The light, there's a wheel on the light. Yes, this one. Yeah. Turn the wheel up or down.
Okay. So, the first thing when people talk about white spaces, they start talking about that is, we're going to get rich, all of us, because spectrum is so expensive, and there's lots of spectrum in the white spaces, so we're going to be rich, so let's work on it. I am sorry to say, and it'll become apparent in this talk, that white spaces also have their limitations. So I don't know if we'll get rich after all. So we'll start with a definition of white spaces. So, white spaces are really the empty TV channels. So, just to put a few numbers, we're ranging from channel 21 to channel 60. For that's 470 megahertz to 790.